continuity and differentiability. These are two big ideas. These are two basic ideas that we see show up again and again and again. You have to have a deep understanding of what it means for a function to be continuous and what it means for a function to be differentiable so that you can use some of these other theorems later on. Some of these important theorems that we've studied in the past that involve continuity and differentiability. Let's get some hands on this. Theorems that you've studied in the past that have something to do with continuity or differentiability. I can think of at least three. Name theorems having to do with continuity and differentiability. Go for it. Give me one of them. Giselle?
Oh, me?
Yes.
Mean value theorem.
Mean value theorem. In order to use the mean value theorem, the function has to satisfy two conditions. It has to be continuous and differentiable. Give me another name theorem. We've already got mean value theorem. There are other ones with names. Abraham. IVT. The IVT, the intermediate value theorem. What does the function have to be in order to use the IVT? It has to be continuous. There's at least one more. The IVT and the MVT, these were the two big ones. The what?
Does it have a VT in it?
It has a V and it has a T. It also has an E. The extreme value theorem. What does the extreme value theorem say? Huh? You looked in the index. What a show off. The extreme value theorem. If you have a continuous function on a closed interval, there is always a highest point and there's always a lowest point. Those highest points and lowest points are either inside the interval or they're an endpoint, which is why we always check the endpoints. Now I want to stop talking for a little bit, give you guys 2 minutes to just refresh yourselves here on the processes. Continuity and differentiability sometimes show up on the free response, and this is where the notation is lethal. Multiple choice, nobody checks your notation. Free response, you've got to get this under control. So I want to spend the next 22 minutes working through a model problem, going over the notation. Take some time to read, I'll pick up the steps. More rain. At least we'll be trapped Deep breathing. I'm on all the things. Mariah. Fabricia's another class. Naomi. Giselle.
What if I already did?
You already got it? Great. Nora.
What?
Gabriel.
Yes or no?
Yes, sir. Depending on the weather.
Yeah.
I can do 4 questions in like 1 minute.
Good. All right. So way back in the day, back in August, we would do power teaching all the time, and you guys would get up on your feet, and we had all the hand motions, and we had all the things, and that's what we're about to do right now. So everybody get up on your feet. Up, up. And I have worked with seniors long enough that I know there's no way on God's green earth you remember all the moves since back in the day. For those of you that this is how your brain works, I apologize for not doing this enough. Jose, how you doing? I think come on over.
What?
For those of you that don't have a brain that works like Juan's does, the words are up here. Okay. In order for a function to be continuous, why are we doing this?
Because you don't get continuous.
This goes back to like the 8th grade definition of continuous, right? Now please keep it a function. Don't let it like swirl back on us. A continuous function. In order for a function to be continuous, you know this, there can be no holes. There can be no doors are up there. Really. There can be no jumps. There can be no breaks. And there can be no vertical asymptotes. The whole is considered a removable discontinuity. Now, real quick, you know that your function's going to have a hole if you see something like this guy right here. This function here has some discontinuities. Where am I going to have discontinuities?
Plus a -2.
Okay, I'm going to be discontinuous of some sort. Discontinuous. X equals -2 and x equals 2. Because that's where the denominator is equal to 0. But one of these is a removable discontinuity. Let's get some hands on this. Which one and why? Which one's removable? Removable, they're using this word for a reason. And why? Just from here? You get a 50-50 shot here. Jasmine, which one?
Is it -2?
-2 is the removable discontinuity. Do you know why?
It's stated twice. Well, it appears twice.
So tell me more.
So that means that you can have it at 2 different places on the graph, which means it may be a break or a jump.
That's actually not why it's removable. You have the right discontinuity. X equals -2 is removable. Why? That x plus 2 is a factor in the numerator and it's a factor in the denominator. So what you can do is you can simplify to the function 1 over x minus 2, and by this cancellation, it's this cancellation that tells me removable. All right, are we okay there? Yeah, totally not awkward at all. The whole thing on camera. Yeah. Okay, so I would expect you guys know a whole lot about continuity. But there is a 3-step process. You have to know all 3 steps, and this is where you guys start leaving points on the table. If you're going to show that a function is continuous at a point, there you go, at a point, the function has to satisfy 3 conditions. Number 1, f of c is defined. It just means I can plug in. That's it. Number 2, the limit exists. We had hand motions for this. Limit exists. Limit exists. You might want to look at Jennifer. She remembers limit exists. We're doing this thing, right? You have to check the limit from the left and the limit from the right. They have to be equal to each other. Is that enough for continuity? The function's defined and the limit exists.
One more.
Right, it's possible that the limit exists, but you have a hole. And the function's defined up here. So if the limit exists, you could have a hole. The function's defined up here. Would you guys say this is a continuous function?
No.
No. How do I make sure it's a continuous function? F of c and that limit have to be the same. Okay? All 3 steps. The function is defined. The limit exists, but there's no hole. That's why we need to close it up. Okay? 3 steps. Now let's go on a little bit further with differentiability. No, stay standing. It's only another minute. You can do this. You're strong. Okay. All right. In order for a function to be differentiable at a point that is smooth, like I am smooth, not round, smooth. It's a different word. The function must be continuous, and there can be no, favorite word ever, there can be no cusp points. Cusp point, right? Right, not oscillation. God, no. Oscillation is end behavior. Cusp point means sharp. You also can have no vertical tangent line. Think end of a circle, right? The tangent line would be perfectly vertical. So if I look at this first graph over here, okay, what do we think about this first graph? Clearly not continuous at x equals 0. Is the function defined? Is the function defined at 0? It is defined. There's a point there. Does the limit exist? Right, limit from the left is something, limit from the right is something else, not continuous. If I'm not continuous, Daisy, you're okay with not continuous? What do we know about differentiability?
It must not be differentiable.
Right, if the function's not continuous, I can't be differentiable. There's at least one other place where you should be questioning differentiability. At the cusp point. At a cusp point, this guy over here, you cannot be differentiable. And depending on your eagle eyes, you might see that there is sort of a vertical tangent line happening over here. They're really hard to see on a graph. You want to think like end of a circle. That's where it would fail to be differentiable. Everybody good? We got continuity. We got differentiability. All right, have a seat. Let's do it. All right, we've only got 12 minutes. Thanks, Giselle. You're in my mind and my heart. You know exactly what I need. Okay, for those of you that feel like you've got a good handle on continuity and differentiability, go. Fly. Fly, little monkeys. Okay. So for those of you that are not 100%, we're going to go over this step by step and get all the notation right. Jose, focusing on the notation here. Okay. For those of you that are with me, I want to show that this function is continuous. There is a place that you should know to check continuity. Where's the place? Adriana, where are we going to check continuity? We have to check continuity at x equals 1 because that's where my function switches. Don't worry, it's going to be okay. Now, 2 cosine pi x. Is that a continuous function? Cosine function is continuous. If I stretch it vertically, compress it, still continuous. So I know that this function is continuous for x less than 1. Now, e to the x, continuous? E to the x, yeah, that's continuous, right? E to the x minus 1 just says shift it 1 space right. Minus 3 says shift it 3 spaces down. So if I know about this function, I know that it's continuous for x greater than 1. Cosine is continuous for x less than 1. This guy over here is continuous for x greater than 1. The only thing stopping this function from being continuous everywhere is to have a conversation, am I continuous at 1? Right, this is what we care about. So we go through the process. And the first step in the process, David?
What I did was plug in into the equations to see if there is
Right, I need to know, does f of 1 exist? Now you said plug it in, now you got to plug it into the right one. Which one, David?
So,
First one or the second one? For x equals 1, which one? Has to be the second one because x is equal to 1. I'm going to use this one. So Jose, all I need to see on your paper is you're going to say e to the 1 minus 1 minus 3. 1 minus 1 is 0, e to the 0, 1. 1, e to the 0, minus 3, negative 2. That just shows me the function is defined at x equals 1. The function exists. Not enough for continuity. Your next move has to be
And the limit.
we bring on those limits. And it's been a while since we brought on the limits. I'm going to check to see, does the limit as x approaches 1 exist? Now, for some functions, you can plug in the 1 and that's good enough. But when it comes to a piecewise function, and you've got a break at 1, you're going to have to find the limit as x approaches 1 from the left. You're going to have to find the limit as x approaches 1 from the right. Well, let's do it. Limit as x approaches 1 from the left. If I'm to the left of 1, that's a number like 0.9, 0.99, 0.9999999. First function, second function. First function. So evaluate that limit of the first function, 2 cosine pi x. Now it's been a while and maybe we're going to get a little tripped up here. All you need to ask yourself is what happens as x gets close to 1? How close? Super close. So close you can't tell the difference anymore. So close that we're just going to try plugging in. And so you get 2 times cosine of pi. Although we don't normally simplify, you're going to need to know what the number is. Cosine of pi, negative 1, 2 times negative 1, negative 2. I'm feeling pretty good. Not done, that's just limit from the left. Now you go after limit from the right. The limit from the right, now I've got to use the second function. Limit as x approaches 1 from the right of e to the x minus 1 minus 3. Eunice, can you give me some examples of numbers bigger than 1? Like getting closer to 1 from the right? Right, 1.1, 1.001, 1.00001. That's what we're thinking about, but what we're going to plug in, 1. And we're going to see what happens. So we get e to the 1 minus 1 minus 3. I think we've already done this and you guys know the answer. Should be negative 2. Conclusion?
It is continuous.
Continuous, right? You could go and say, oh, because of these two, the limit as x approaches 1 equals negative 2. Make that look like a negative. And that's good, but the conclusion has to be f is continuous at x equals 1 because f of 1 equals the limit as x approaches 1. If any of those things had fallen apart on you, can't say continuity. Have to see all the notation for free response. Don't want to see any of the notation on the multiple choice. Spending all the time keeping track of those limits is good for you, but it is a waste of time on multiple choice. Multiple choice, they just want to know, is it continuous, is it not continuous? What's the right value to get continuity? All the things. How's everybody doing? Continuity's okay? Okay, it's been a while. All right, differentiability. We got one more. We've got to determine if f is differentiable. Christian, what do you know if a function's differentiable?
We have to show that f of x is the limit of as x approaches a exists, and then that they both equal each other.
Close. Differentiable. Differentiable means, what do we know?
The derivative exists.
The derivative exists. Okay, that's what it means. And so you have to first be continuous, right? You can't have any cusp points. You can't have any vertical tangent lines. But really it's just a question of, does the derivative exist? And Chris, I think what you're thinking about is way back in the day, we went through the hard problem. we'd say, let's find the limit as x approaches 1 from the left of f prime. Let's find the limit as x approaches 1 from the right of f prime. And the way we used to do it is we'd say, oh, let me do limit as x approaches 1, f of x minus f of 1 over x minus 1. Over here, we do the same thing. We'd say, let me work it out. And I got to tell you, that was like a 15-minute process to go through. You had to find f of x, you had to find f of 1, you had to divide and factor and all the things. So, new color, new idea. If I know what f of x is, if f is 2 cosine pi x, is x less than 1, and it's e to the x minus 1 minus 3 for x greater than or equal to 1, well, take a minute and find f prime for me, for both parts. Use your derivative rules. Make life good for yourself. Okay, derivative of 2 cosine pi x. 2 is a constant, leave it alone. Derivative of cosine? Careful. Negative sine. Pi x times pi, because we got chain rule happening. Derivative of e to the x minus 1 is e to the x minus 1 minus the derivative of 3 is going to be 0. This guy here is your derivative. So all I have to do when I ask the question, what's the limit as x approaches 1 from the left of f prime, go to f prime. Find that limit of 2 negative sine pi x times pi. X gets close to 1. We've got pi. Sine of pi?
0.
Sine of pi, 0. Times 2 times pi,
0.
we got 0. Find that limit as x approaches 1 from the right of f prime. That's going to be limit as x approaches 1 from the right of e to the x minus 1. You get e to the 0, which is 1. Conclusion?
It's not different.
Not it's not.
It's f of x is not
F of x is
different.
not different.
Yeah, so a couple of conclusions. You could say, therefore, the limit as x approaches 1 of f prime of x does not exist, right? The derivative doesn't exist. Better would be to say, therefore, f is not differentiable at x equals 1. Okay. Tonight's homework is like 10 multiple choice questions having everything to do with continuity and differentiability. That was our whole class period. It happened. It happened. You're probably going to find this assignment easier, and that's a good thing. The other thing I need to have happen tonight, because you're going to have a little quiz when you walk in tomorrow, a different kind of quiz than what you've ever experienced before. I need you to look over all the derivative rules. Make sure you know your chain rule, the derivative of the sine, the quotient rule, all the things. Okay?